All right, so we're on day 10. You got homework in the packet, page 1 to 2. If there's not space there, do it on a separate sheet of paper, and then you got a couple from the textbook. So first ones on the homework were some area between polar curves. So the first one wanted outside of the one that's the lower one and inside the upper one. So really what we're looking for is this space here. Notice it's symmetrical, so we're just gonna do the right half of it and then double it. So set them equal to find those intersection points. You end up with sine as a half. So that's a 60-degree reference angle. So they're crossing at pi over 6 and 5 pi over 6. So what we're going to do is we're just going to do it from pi over 6 to pi over 2, and then we'll double them. So you'll do the outer one, the 3 sine theta, minus the inner one, the 2 minus sine theta. Now we're going to have to multiply by 2. I chose to just do that at the end, or you could put the 2 right there in the beginning, your choice. Square them out. Have to do a power reduction for each of them. We'll stop here in case you needed to check your work at all. And then eventually, after you do the multiply by 2, you should get 3 square root of 3. Now, if you had multiplied by 2 just right in the beginning, you would have had the 9 out in front that you would have carried through. And then 1 for the other one, 9 just in the front of the first parenthesis. So the other area one, we wanted outside of that circle, but inside the bigger one. So the thing you had to be careful about here is the big one, it took 2 pi to go all the way around, but that circle, it only took pi to go around. Because cos will get back to its starting point when we have pi comma negative 1. That'll essentially be the same point as 0 comma 1 in cos. So square it out. Again, you had a power reduction that you had to do. Sub everything in. And nothing we had to multiply by here, 5 pi a squared over 4. Then we switch to the new stuff, the arc length. We do our r squared plus our derivative of r with respect to theta squared. Take the square root and then sub in. And we should have got 2a pi for the first one. And we also happen to get 2a pi for the second one. In that second one, 42, it's because you can pull out a square root of 4a squared, and then the cos squared plus sine squared is just 1. So 43 was one you could do in your calculator. You had your original r and then your derivative. Similar idea with 45. You have your original squared plus your derivative squared, and that was a calculator one. Another calculator one for 46. 48 you had to do by hand because you had 2e to the 2 theta, so that's square root of 2 and then e to the theta. Antiderivative e to the theta is e to the theta, and sub in. And that was it for the homework. So today we're going to review vectors, which you should have seen at some point last year. You probably also work with vectors in physics if you're taking physics. So vector is a quantity, it involves two things. It involves a magnitude, so how much, and a direction. We represent it with a directed line segment, so there's some initial point and some terminal point where the arrowhead is. And equivalent vectors are considered those that are the same length and also going the same direction. So in other words, at the same angle. So if we wanted to show whether these are equivalent or not, they're definitely going at the same slope if we did our up and over. So we would just have to check and see if they had the same magnitude. Well, to do that, we're basically just doing a Pythagorean theorem. If we went from 1, 2 to 4, 6, that means this is 3 and this is 4. From 3, 0 to 6, 4, that's 3 and that's 4. So in both cases, we would have 3 squared plus 4 squared. So that'd be 9 and 16, so square root of 25. So we would have a magnitude of 5 for each of those. So these vectors are equivalent. And since each of them went 3 to the right and up 4, we could say that they could both be written in the same component form. Component form is when the initial point is at 0, 0. So imagine if we slid them to start at 0, 0, they would both have the same component form for our vector of 3, 4. And notice how our vectors are written. They almost look like less than and greater than signs. They're kind of pointy brackets. So on the next page, we're going to try and write these each in component form. So basically, you're just seeing how you're moving right and left and then up and down. Well, for this one here, we're moving 1, 2, 3, 4, 5, 6, 7 to the right. And we're moving down 1, 2, 3, 4, 5. And the intent is for the arrowhead to be on the nice value. So 7, negative 5 would be our component form of that vector. It's a little bit trickier when we have angles. So this is a 45, 45, 90 triangle. Normally across from 45, we have d squared root of 2. So if we divide both sides by square root of 2, d is equal to 6 over square root of 2. If we multiply top and bottom by square root of 2, we get 6 square root of 2 over 2, which is really 3 square root of 2. So d is what's across from our 45, so we should have 3 square root of 2. But then this side would be negative 3 square root of 2 because it's going left. So our component form is negative 3 square root of 2, comma 3 square root of 2. So here, this is not one of our special right triangles. Let's call that x, let's call that y. We could say that cos of 20 is equal to x over 4. So x would be equal to 4 cos 20. Similar idea for y. Sine of 20 would be equal to y over 4. So 4 sine 20 is y. Now you would then just have to be careful about if things should be positive or negative in the quadrant we're in. In the third quadrant, both x and y should be negative. So this is really negative 4 cos 20, comma, negative 4 sine 20. Now notice we have degrees here. Vectors are one of the rare cases that you'll work with degrees in calculus. Usually we work with radians because we are taking derivatives, but here is the one rare case where you see degrees. Now the one other way that you could have written this in component form is just imagine the angle coming all the way from 0. Well, that's 20 beyond 180, so that would be 200. So you could also have written this as 4 cos 200, comma 4 sine 200. Because the 200 would then take care of the negatives on its own. So in the box there, we've got operations on some vectors. The 3 in the middle are pretty straightforward. When you're adding vectors, you just add the like parts. When you're subtracting vectors, you just subtract the like parts. The k is often referred to as a scalar constant, and that's just distributing it through to each of the parts. So the first and the last might be the less obvious. So the first one is considered either the magnitude or the speed. It's represented with the double lines there. And you're essentially just doing a Pythagorean theorem where you're getting the hypotenuse by itself. So again, that top one is the magnitude or the speed. The bottom one is what's called the dot product. So notice your answer to a dot product is not a vector. Same thing with the magnitude up on top. Your answer is not a vector, it's just some value. So over on the right, we're going to let u and v equal those vectors. So if we want to start out with 2u, that means we would double each of the ones in u. So we'd have negative 2 comma 6. And then we got to add it to 4 comma 8. So when we add those, add the like parts, we'll get 2 comma 14. Next one, we are multiplying by a half for v. So we'll have negative 1 comma 3 minus. Then if we multiply by a half, we would have 2 comma 4. Then subtract the parts. Negative 1 minus 2 gives us negative 3. And 3 minus 4 gives us negative 1. So if we do v divided by 2, v divided by 2 is really 2 comma 4. And this is saying that we want to do the magnitude for that. Well, 2 comma 4 as a component form vector means we're going to right and up 4. So essentially what we're doing is we're finding that. So we've got the square root of 2 squared plus 4 squared. That would be 4 and 16, which gives us square root of 20. And that's 4 times 5, so we have 2 square root of 5. And that would represent either the magnitude or the speed of v over 2. So over on the next page, we're going to find the angle between the vectors. So negative 1, 5 is this one here on the left, because you went left 1 and up 5, and 5, 2 is the one on the right. So we're actually going to show you 3 options, even though it only says 2 options there. So we want to find this angle between. Well, let's think of it as 2 separate right triangles. And we'll just find each of the angles at the origin using right triangle trig. Well, in the blue triangle, to find that angle, we'd have to do an arctan. Arctan of our opposite, which would be 5, over our adjacent, which would be 2. Plus the arctan for that red one, where the opposite is 1, and the adjacent is 5. So if you put that in, our calculators are probably in radians, and you get 1.388 radians. But with vectors, you usually tend to see things in degrees. So we would want to then multiply that answer we got by 180 over pi to convert it to degrees. And to 3 decimal places, we would get 79.509 degrees. So that's option 1. Option 2 is we could imagine this is connected, and we can do a law of cosines. Well, to do a law of cosines to find this angle, we would have to know all 3 sides. Well, that right-hand vector, we went 5 right and 2 up. So if you do a Pythagorean theorem, that's going to make this be square root of 29. For the left-hand vector, we went 1 left and 5 up. So from a Pythagorean theorem, that's going to be square root of 26. Now to figure out the length of your other one, imagine it's the hypotenuse of a right triangle for a second. This would be 3. This would be 6. So 6 squared is 36, 3 squared is 9. Put them together, you get 45. So this is square root of 45. So doing a law of cosines, we would have our c squared, so that'd be square root of 45 squared, is equal to our a squared plus our b squared minus 2 times a times b cos of our angle, which we don't know. So if we square the 45s, the 29, and the 26 and subtract them over, on the right that would be 55, so subtracting it over would give us negative 10. And if we divided that over, we would get 0.182 and change equals cos theta. Taking your inverse cos, you'd get theta equals 1.388 because our calculator is probably in radians. And notice that matches our radians from before, so in degrees, this would be 79.509 degrees. Again, because these tend to be in degrees when you work with vectors. So that was option 2. Option 3 is something I think you saw last year. If you want to find the angle between two vectors, theta is always equal to cos inverse of u times v over the magnitude of u times the magnitude of v. So in this case, we would have cos inverse. Our dot product, if we go back, you multiply the x parts and then add your product of your y parts, and it gives you some value. So if we take our x parts and multiply them, we get -5. If we take our y parts and multiply them, we get 10. So -5 and 10 would give us 5 in the numerator. Our magnitudes of u and v, we already knew, were the radical 26 and the radical 29. And then we would just do inverse cos of that, which, if we peek over to here, notice that's going to be the same value, because if you divide the -2 over, you get 5. And then you'll have 5 divided by those two radicals. And then you're doing the inverse cos. So it ends up working out exactly the same. So this eventually, as a degree value, would also give us 79.509 degrees. So it's your preference of what you would like to do to find an angle between two vectors, but those are the 3 options we have. So our last one for this video, we'll look at an application problem. So we got an airplane that's going 500 miles per hour, due east. The plane hits a 70 mile per hour wind. It's blowing in the direction 60 degrees north of east. So when you say north of east, you take east, and then the angle is going north from that. So our angle would look kind of like that, where this is 60 degrees. The plane holds its compass direction, but because of the wind, the plane has a different speed in different directions. What are the new speed and direction of the plane? Well, remember, speed is just magnitude. So we'll just have to do our magnitude calculation. And the direction should be the degree of theta. So here's kind of a picture what we have. It was going 500 miles per hour due east. So our speed, that was our speed or our magnitude, and the vector is showing us the direction. The speed or the magnitude of the wind is 70, and it was acting at 60 degrees north of east. That purple line, the resultant, is the new path of the plane after the wind. So vector P we can define as 500, 0, because it went 500 to the right and none up and down. For vector W, this is a 30, 60, 90 triangle. Across from the 90 should always be 2D. So D is just 35. Meaning across from our 30 is 35, and across from the 60 is 35 radical 3, because they're D and D radical 3 respectively. So our vector for W we can write as 35, 35 square root of 3. So we can represent our resultant vector by adding those vectors together. So 500 plus 35 gives us 535. And then adding the y's, we get 35 radical 3. So that is telling us that this distance here is 535. And this distance here is still 35 square root of 3. So our speed of the plane is the same as the magnitude, and that's just the length of that hypotenuse if we think of it as a right triangle. So that's just going to be 5 square root of 535 squared plus square root of 35 square root of 3 squared. And if we punch that in the calculator, keep it to 3 decimal places, we'd have 538.424. And our units we have is miles per hour. Now for the direction of the plane, we're looking for that angle in degrees. Probably the easiest way to do this is just do a quick arctan. We can do arctan of our opposite, the 35 square root of 3, over our adjacent, which was 535. Remember, your calculator is probably in radians. So go ahead, punch that in, get your radian value, and then multiply it by pi, or by 180 over pi. See if you can find the degree value to 3 decimal places. And then you also have to tell it with compass directions. Are we east of north? Are we south of west? Are we east of south? So see if you can put a description on that as well. So pause the video, punch that in, and then a question's going to pop up for you to have to type in both your degree value to 3 decimal places and what you would have in terms of compass directions as well. So we should have gotten a degree value of 6.465 degrees. And based on where our angle is, we would say that that is north of east. Now, if you had said the complement of that, so like this angle here, then that would be described as east of north. So you could say it's that degrees east of north, but most likely based on the triangle we have set up, we would find the 6.465 and do it as north of east. That's it for today's video. So you got day 10 homework. Have a great rest of your day.